Hello, Mr. Hasty here. Today we're going to be talking about machines and efficiency. So we're going to start off with a few definitions. A machine is any device used to change the direction or magnitude of force. So when we talk about machines, we usually start by talking about the simple machines. The 6 simple machines are shown here. The lever, for instance, number one, it changes the direction of the force. You apply the force down, it applies the force up. And based on where you place the fulcrum, it can change the magnitude of the force as well. A pulley affects the direction of force. Usually you apply a force down to result in a force going up. The wheel and axle, we're generating a force around the distance of the axle to generate a different amount of force around the distance of the wheel. Inclined planes, we're looking to move an object upward, but we settle for using less force over a longer distance to move it up the ramp. And a wedge does that in reverse, essentially. It directs the force. We direct the wedge in a direction, and the force is directed downward. Same with the screw. We direct a force downward, and it directs the force in a circular motion. All right. Now, when we talk about machines, we talk about those simple machines. We also talk about a complex machine. And a complex machine is just a combination of simple machines. So if we think about a bicycle is a good example of a complex machine. It involves a wheel and axle, clearly, to turn the wheels. It involves levers used to move. The handlebars themselves are levers. The pedals themselves are levers. And so it has a lot of these. You could view the chain and axle as a pulley system. And so all those combinations together make one larger machine. So whenever we talk about machines, we always talk about what's going into the machine, what's coming out of the machine. So the effort force is the force the user inputs. And the resistance force is the force the machine outputs. So, in our lever example, when we push downward, that's our effort force, and the force generated by the lever upward would be our resistance force. All right, I'm going to move on. So the reason we use machines is to change the magnitude or direction of force. So we have specific terms that we like to discuss when working with this. The first is mechanical advantage. Mechanical advantage is the ratio of output force to input force. So as a formula, mechanical advantage would be viewed as the force of the resistance, Fr, divided by the force that we effort, the effort force. Now, in a perfect world, uh, we wouldn't lose anything when we used a machine. We wouldn't lose anything, but we do. We lose a lot of potential um, force due to things like friction and our machine having bend or warp. When you use a lever, for instance, that lever might bend slightly, and then that bend is reducing the amount of effective work you can do. So, when we talk about mechanical advantage, we like to compare it to what would be an ideal mechanical advantage. Now, an ideal mechanical advantage is the ratio of displacements. So, for instance, with a lever, how far do you push that lever down versus how far up the resulting object goes? So, the formula for ideal mechanical advantage is the effort distance divided by the resistance distance. So, that'd be how far we push it over how far it moves. So if you have a lever and you push that lever 2 centimeters and it only went up 1 centimeter, we would have an ideal mechanical advantage of 2. No machine ever perfectly meets its ideal mechanical advantage, and the relationship there is what we call efficiency. Efficiency is essentially how close do we get? And there are 2 formulas for efficiency. The first formula for efficiency is the work we get put in divided by the work we get out times 100. And that's just to turn it into a percentage because efficiencies are usually labeled as percentages. We could also do it as the mechanical advantage divided by the ideal mechanical advantage times 100. So there's 2 formulas for efficiency depending on what information is more at hand. If we have the calculations for work at hand, it's easy to do it with the work formula. If we have the mechanical advantage and ideal mechanical advantage, we can use that formula. So that's quite a few formulas at once. So let's go ahead and put those in practice. So this first example, we have a person exerting 450 newtons of force on a lever, pushing it down 1.2 meters. The lever then exerts 575.0 newtons on the target object, lifting it only 0.85 meters. So what we're going to do is we're going to talk about the mechanical advantage and efficiency of this system. So for part A, it wants us to find the ideal mechanical advantage. So the formula for ideal mechanical advantage is effort distance divided by resistance distance. So the effort would be the distance that we moved the lever, which would be 1.2 meters, and the resistance distance would be how far it moved, which is 0.85 meters. Now notice that the meters here are going to cancel, and this is an example in physics of something that's actually a completely unitless value, which is kind of rare. Usually we have units on everything. This will be one time where we don't. Restricting ourselves to 2 sig figs, we have 1.4 as the ideal mechanical advantage of that system. So what that essentially means is ideally it would multiply our input force by 1.4 times. So part BS, what is the actual mechanical advantage? Well, we can actually look at what the actual mechanical advantage is. So the mechanical advantage is calculated as our resistance, wrong value there. our resistance force divided by our effort force. So our resistance force is how much the machine produces. It produced 575.0 newtons. And our effort force, how much we put in, was 450 newtons, which restricts us to 2 sig figs, but again, we'll work with that as it is. And I get 1.27 repeating, which rounded appropriately here is 1.3. Now it's important to note that those are rounded values because when we do part C, we'll need to actually go back and use the real values or very, very close approximations because we're going to ask for the efficiency of the system. Well, efficiency, since we have mechanical advantage and ideal mechanical advantage, is most easily calculated as mechanical advantage divided by ideal mechanical advantage times 100. And so in this scenario, I'm going to have 1.27 repeating divided by 1.41176, basically the unrounded version from part A, multiplied by 100, and we get, as a percentage, to 2 sig figs is what we're restricted to, 91% efficient. Now let's speculate real quick about why this would happen. So in this case, if we have a lever, theoretically, if we're moving a lever to increase force, we have a shorter end and a longer end where we're applying the force. And so that generates an ideal situation, but the force doesn't actually work out. And that might be because as we push the lever, if there's substantial weight on the end, our lever might start to bend. And that bend in the lever can create a loss of force. That force might also be translating into the fulcrum in some way, creating friction in some way, and so we lose a little bit when we do something like that. So example 2 here is going to be a bit tricky. A bike wheel has a radius of 42.2 centimeters, while the gear operating the wheel has a radius of 4.25 centimeters. The chain exerts 175 newtons of force, and the wheel rim moves 15.0 centimeters. If the system has an efficiency of 95.0%, determine the following. So before we do this, let's talk about the system a little bit. What we have is a larger wheel being moved by a gear. This is essentially a wheel and axle, except instead of calling it an axle, we're calling it a gear. So part A says to find the ideal mechanical advantage of the system. Ideal mechanical advantage is calculated as the effort distance divided by the resistant distance. Now, what is the effort and what is the resistance distance? The effort, where the force is coming from, the axle, is actually the distance around the axle, which would be the circumference. So we could calculate that as 2 pi times, and we could do this in centimeters, but we're so used to converting everything to meters, I'm going to do it that way. Divided by the distance out, the distance around the wheel. So the distance around the wheel, ideally, is 2 pi times 42.2 centimeters, or 0.422 meters. So we do that calculation into 3 sig figs, we get 0.101, and that would be useless because it is a mechanical advantage. Now I want you to note that the 2 pi's could have canceled there, so instead of doing the ratio of the circumferences, we could have just done the ratio of the radii and gotten the same information. So for part B, it wants to know the actual mechanical advantage of the system. Well, normally to do mechanical advantage, we do the formula, resistant force divided by effort force. But that's not going to work in this case. We know the effort force. The chain has a force of 175 newtons, but we don't know the resistance force. So we need to find another formula that involves mechanical advantage. And since we know the system's 95% efficient, we can use the formula for efficiency, which is mechanical advantage divided by ideal mechanical advantage times 100. So I'm going to rewrite this formula so that it is solved for MA. So to do that, I'm going to divide efficiency by 100 to get rid of the times 100. And then I'm going to multiply by the ideal mechanical advantage. Now, why don't I want to just plug in numbers here? Well, this calculation is going to involve the ideal mechanical advantage we already calculated, and we cannot use that rounded value. So what we have to do is, we know the efficiency is 95.0. The 100 is a perfect number, but we can't just plug in the 0.101, that would throw off our rounding. So we actually have to plug in the calculation we used to find the ideal mechanical advantage. If we don't do it this way, our accuracy will get thrown off heavily. So we're going to get, rounded to the appropriate number of sig figs, 0.0957. All right. So on to part C. I'm going to clear this. So for part C, it wants to know what is the resistance force in this scenario. So we know the force that was exerted, that's 175 newtons from the chain. So how can we find that? Well, we can use our formula for mechanical advantage, which we just calculated, is resistance force divided by effort force. Now we're looking for resistance force, so we can solve for that. The resistance force is mechanical advantage times effort force. Now we know the effort force, but we actually need to go back and use the unrounded version of mechanical advantage. So I'm going to take that out of my calculator and take whatever value I got from my mechanical advantage and multiply that by 175. And when you do that, you're going to get 16.7 newtons. And that makes sense. Our mechanical advantage in this situation is 0.0957. It means that the amount of effort we put in is going to be severely reduced. So we're going to put in 175 newtons and we're only going to get 16.7 out. All right, part D. How far was the chain pull to move the rim 15.0 centimeters? So we talked about the ideal mechanical advantage, moving the ideal full axle rotation to the ideal full wheel rotation. But we're going to use our ideal mechanical advantage to do a very specific thing. We knew that the wheel rim moves 15 centimeters, so we're going to figure out how far that moves the chain. So our formula for ideal mechanical advantage, which we calculated earlier, is effort distance divided by resistance distance. Now, here we're looking for how far the chain was pulled. That's our effort distance. So our effort distance is the ideal mechanical advantage times the resistance distance. So we have to go back and again use the full value. We can't use the rounded value, but our resistance distance is the 15.0 centimeters. So we'll call that 0.150. We do that calculation, we get to 3 sig figs 0.0151, and that'd be measured in meters. But since everything else in this problem is in centimeters, let's convert it back. 1.51 centimeters. The concepts of efficiency and mechanical advantage can be pretty straightforward, but when you're in the midst of the calculations, you can kind of lose sight of exactly what's going on. Mechanical advantage is essentially how much is our force multiplied by. In a lot of situations, our force is multiplied to a higher degree. In some situations, it's multiplied below 100%. And usually the reason we're taking that trade-off is to make a simpler or easier path for ourselves in the long run. But no machine, no matter what, is 100% efficient. Efficiency is always lost through bend or warp in the machine, friction, or a loss of force being applied in the directions we want it applied in. And so no machine will ever have 100% efficiency. If you ever get 100% or greater than 100% for the efficiency of your machine, you know you've done something wrong in your calculations. All right, see you next time.